Okay, so in this lesson, we're going to talk about going through the super heterodyne receiver and all its main components. Okay, so some of the so at the beginning of the lesson, we talked about receiving and what the minimum criteria for receiving was. We saw that as far as the earlier stages of AM reception, we had something called a TRF, or a tuned radio frequency receiver, right? The key difference between the tuned or the TRF and the super heterodyne receiver lies in the fact that we have this extra stage right here. Okay. Now the problem with the normal AM reception is when we have an RF stage and a detector stage. Right? And then the audio. So the problem with the normal TRF is that every single time I wanted to receive a new frequency and a new channel, I would have to manually tune the capacitors or inductors in the tuned portion of this RF stage to be able to receive the signal every single time. Okay. What this led to is that we weren't really able to totally fine tune that to get a nice received signal. Okay, so the super heterodyne receiver fixes this by adding this concept of injecting a local oscillator frequency into a mixer and having an IF amplifier that's at a fixed frequency and never changes. Okay, so we receive our signal, right? Now keep in mind we have what's called a gang tuning. Okay, in the old days we had this big dial that would tune capacitors, but in modern electronics we have varactors. Okay, so when you tune this guy, chances are you're tuning some sort of potentiometer that's changing the potential across the varactor, changing the tuning of because if as you know, if you change the potential across the varactor, you're changing the capacitance. So that's how the tuning's done. Notice that the tuning gets done in the first three stages: the local oscillator, we'll talk about why in a second, the mixer, and also the RF stage. Now, why it's done at both these stages has a lot to do with the amplification and the fine tuning, because there is some gain in the mixer stage. You'll see that we basically get gain throughout the super heterodyne receiver with the exception of the detector. The detector is the only one that really costs us as far as gain is concerned. Okay? So we receive our signal, we have a tuned amplifier, we're tuned to our frequency, we pick it up, right? This is an amplitude modulated signal. It has a carrier frequency, it has a lower sideband and an upper sideband, okay? Now, in the AM transmission lesson, you should have learned that AM modulated signal, it has the intelligence hidden inside, okay? But if you had a spectrum analyzer, you wouldn't actually see it, okay? The intelligence is hidden between the addition and subtraction of the lower and upper sidebands with the carrier frequency. So in order to see the big picture, what we need to do, because remember, and I can't remember what it was, but say our IF frequency was tuned at 455 kilohertz, which was pretty standard tuning. So whatever this frequency you're receiving, right? If it's high side injection, now let's get into what's going on, right? That receiver, this guy's going to tune it and amplify whatever the amplitude modulated signal is. We're going to go into a mixer, okay? Then we have our local oscillator that's going to inject another frequency and mix it with that amplitude modulated signal, okay? This is kind of like remodulating the signal again, okay? And when we do that, we end up with something like this, okay? We get the mixer, so whatever our signal, so you can see at this case, the IF is tuned for that 455, plus or minus the 1 kilohertz. And then our carrier frequency coming in is 1,000 kilohertz here, and then plus or minus 1 kilohertz, okay? Which tells me that the intelligence is actually 1 kilohertz. Our local oscillator frequency, if it's high side injection, will be the whatever the receiver signal is tuned to plus the IF amp. that's what your local oscillator frequency will be. And you can see that in this case, we have 1,000 plus 455, that's 1455. If it's low side injection, it would be this minus that. Okay, so it would be 1,000 minus 455, okay, which would be 545. So again, that's the difference between high side and low side. And you can see what happens with when we go into the mixer, we develop all these frequencies, because when the amplitude modulated signal comes in and mixes with another frequency, we get again the addition, right? So this 1455 plus and minus the 99 kilohertz, plus and minus the 1,000, and plus and minus the 101. And that's what you see here, okay? You have the original plus or minus so when you subtract, so what's showing here, if you subtract minus so 1455 minus the 99, you're at 454. The 1455 minus the 1,000, you're at 455. The 1455 minus 101, or sorry, 1001, you're at 456, okay? And then you can see our original frequencies, which are here. We have our original oscillator. Then we have the addition of each one. Again, the 99 plus 1455, the 1,000 plus 1455, and the 1,001 plus 1455. Okay. Now what happens is that the IF amp is only tuned for these guys. Everything else, right? So the IF amp is only tuned to these guys. And the trick here is that we keep the IF amp always the same. Always the same. As we're tuning what to receive, our local oscillator is almost adjusting. So it doesn't matter what comes in here. We're always going to adjust this guy to be 1455, meaning the IF will always see this 455 frequency, okay? Because he's always a variable of the two combinations between the RF and the IF, okay? So at this point, all these other stuff gets cut out, and now the IF just amplifies that. So if we